he just put out he'll send you the he goes, everything's good, but hey, you haven't got it. I was like 150 words on the it's just like, don't call it sign like that. I was working on essays because I'll take it.
Hello, everybody. How are we doing tonight? Tired. Tired? Yeah. It's okay. You can get some sleep tonight and then study for the next 2 days. No, we have to do what, circuits tomorrow? Okay. Oh, perfect. So circuits is done. You only have this to worry about. Great. We have the best time. But anyway, so you guys got plenty of time to study for this, which is fantastic. But in case you guys don't know who I am, my name is Jake Shoza. That's my name, that's my email. I'm a brother in SigEp, and this is the DiffEq Final Review Part 2. You guys were here on Saturday night, I think it was. We did a review from Test 1 and Test 2 material. Tonight we'll be doing just the heat equation and the wave equation. It's going to take a while. These questions are long. But we'll do one example of the heat equation, one example of the wave equation. They're very similar. One small difference just adds on one step to the wave equation. But we'll go through that. And then part 3 is going to be on Wednesday night, so the night before your test, same time, 6 p.m., same place in here. And it's just going to be any questions that you guys have. I won't bring anything prepared, but any questions, any problems that you guys have at last minute, come bring those and I'll answer any questions that there are. Sound good? Cool. So I once again want to thank SITTV for being here, recording every review this semester, so that way everyone who takes this class in the future can have those to refer back to. So thank you very much. But with all that, I already wrote our first problem on the board because it takes a little while to write, but we're going to be doing a heat equation. So we have our equation right here where it's saying U sub T is equal to 3 times U sub XX, where we have some boundary conditions, we have an initial condition, and then we know that we're just trying to find what is U when we know that U is a function X times a function T. So there's a reason why you haven't had one of these questions on a test up to this point, and it's because they're very long. Think of these questions as basically most of the stuff that was on test 3, but all now put into one question. So the first step for this is going to be using separation of variables for PDEs. So when we get to that separation of variables, we're going to get 2 differential equations, 2 ordinary differential equations. And for our heat equation, one's going to be first order, one's going to be second order. The second order problem, when we try and solve that one, we end up turning it into an eigenvalues problem. So then we take that equation, and that's the input to our eigenvalue problem. We have to do our case 1, our case 2, our case 3. Eventually, case 3 is where we get the answer that we care about. And then we do all the steps for the eigenvalue problem. We get our solution for that. And once we have our solution for that, now we need to apply our initial condition to figure out what those constant values are. So in some problems, you might have seen them on some of your homeworks or on written homeworks or online homeworks. Sometimes your initial conditions are given in terms of a Fourier series. The good news is most of the time, or on all the finals I've seen, they're not given in terms of a Fourier series, so you don't have to worry about that. But that is a possible next step where the solution to your eigenvalue problem now becomes the start of a Fourier series problem. So it's really just wrapping up all of our favorite topics all into one question. But with all that said, we're just going to jump right in. If you fill out that form for the review notes, I also put the link in the GroupMe, then I'll send you out these notes when I'm done. And this has a step-by-step walkthrough of every step that we're going to do to solve this problem. I don't have the wave equation solved out, so You guys won't be able to check the notes from that, but we'll be doing that after this, and I'll be solving it with all you guys so we can figure it out together. But without further ado, we can get started on the wave equation. The very first step is, I don't like dealing, we know that the first thing we're doing is separation of variables. So we're going to do the same steps that we do for separation of variables. And the first step is, I don't like dealing with that u sub t and u sub xx. So I'm going to rewrite it in terms of my capital T's and my capital X's. Where I know that function u, when I take the derivative with respect to t, is just going to give me a capital X times capital T prime. And that's going to equal 3 times capital X double prime times capital T. So once I have this, I want to divide everything by u. So I divide everything by capital X capital T, with the thought in mind that this is going to get all of one variable on one side, all of the other variable on the other side. And what we see is our x's go away, our t's go away over here. We have t prime over t is equal to 3 times x double prime over x. Now, we have this coefficient 3 that we can leave it wherever we want. So we can leave it either in the numerator here, or we can bring it over to the denominator here. Either way will work, but I'm going to suggest that you bring it into the denominator just because, or you bring it to whichever term doesn't have your x double prime, or doesn't have the double prime. Because your double prime is what's going to turn into an eigenvalue problem, so the simpler we can make this, the easier it's going to be later on. So I'm going to take this 3 and divide it over to the other side. So now that I have my variables separated, I have t prime over 3t is equal to x double prime over x. At this step is where we bring in that lambda value. So I'm going to set this equal to negative lambda. And now that I set it equal to negative lambda, I can create 2 different equations. So I'll create one equation from here and one equation from these 2. So I have t prime over 3t is equal to negative lambda, and I have x double prime over x is equal to negative lambda. So from those, I can write an ordinary differential equation for each one. So I multiply the 3t over, and then I add it back to the left side, and I get capital T prime plus 3 lambda capital T is equal to 0. And for my x's, I get x, or capital X double prime, plus lambda x is equal to 0. So now I'm going to bring it up here. So we have our capital T prime plus 3 lambda t is equal to 0. And then here we have our capital X double prime plus capital lambda times capital X is equal to 0. So now we have 2 ordinary differential equations. So now we can use all the methods that we've learned throughout the year to solve these ordinary differential equations. So we notice that these are all homogeneous, right? The right side is 0. So to solve homogeneous, I can do my auxiliary equation. So let's start with our easier one first. Now I have a t prime, so this is going to be m to the first power plus 3 lambda is equal to 0, which means that I know that m is going to be equal to negative 3 lambda. So I know that the form for this answer, so t, my function t, is going to equal some constant, c1 times e to the negative 3 lambda lowercase t. So remember, the idea of this whole problem is I want to find some function t and some function x that I can multiply together to get my function u, that it says all the way at the top, because x times t is u, and that's what I'm looking for. So I'm already theoretically halfway there, right? I just solved for what my t is. Now let's solve for what our x is. So I set up my auxiliary equation. I get m squared plus lambda is equal to 0, which means m squared is equal to negative lambda, which means m is equal to plus or minus the square root of negative lambda. But now I ask the question, okay, what form of my solution does this go in? Which form am I homogeneous? And I don't know, because I had a square root. And this is where we start our eigenvalue problem. Because we need to see what are the possible values that lambda can be that gives this a solution. So I'm taking this, and now I'm entering an eigenvalue problem. So I'm just going to start right on, and we'll go on this board. What do you mean? Wait for the wave equation. So the question was, can we get both of them to be an eigenvalue problem? In our heat equation, no, because we only have one second derivative and one first derivative. And you can only get an eigenvalue problem when you have a second derivative, because that's what leads to the m squared, which leads to the square root. In our wave equation, both of them are a second derivative. So they're kind of both eigenvalue problems, but you only have to solve one, and the answer to that you plug into the other. You'll see that once we get into the wave equation. But we now are at this point where I have the equation of x double prime plus lambda x is equal to 0, and I have m is plus or minus the square root of lambda. So now I need to test all of my cases. So let's start with case 1. Case 1 is a good place to start. So I'm going to, square root of negative lambda. So case 1, I'm going to say, what if everything underneath the radical is equal to 0? So negative lambda is equal to 0. Well, that means I have m is equal to plus or minus the square root of 0, which means m is equal to 0, and I have the case with repeated roots. So I get my, not y, I get my function x, capital X, is equal to c1 e to the 0x plus c2x e to the 0x. And I know that my e to the 0x can just go to 1. So I have x is equal to c1 plus c2x. So this is capital X is equal to c1 plus c2 lowercase x. Now, what do we do next in our eigenvalue problems? Well, we plug in our boundary conditions in order to find if we can get a solution for that c1 and c2. So now is when we look at the boundary conditions. And if we see those boundary conditions that it says u sub x evaluated at 0 comma t is equal to 0, and it says that u sub x evaluated at 4 comma t is equal to 0. So what that means is when I take my function u and I take the derivative with respect to x and plug in 0 for x and leave t as its own variable, then I know it's going to be equal to 0. So since I'm leaving t as still the variable t, I know that this isn't going to have any effect on that boundary condition. The only thing that's going to affect that boundary condition is my function x. So I can take those boundary conditions and plug them in for just my x and ignore my t and just leave that on its own. So that's what we're going to do. So I have my function x, c1 plus c2x. And I see that both of those boundary conditions are evaluated for the derivative with respect to x. So I'm going to take this derivative. So I get capital X prime is equal to c2. That's nice and easy. Now let's plug in those boundary conditions. And it says when x is equal to 0, when my variable x is equal to 0, my function is equal to 0. So I get 0 is equal to c2. And then when I plug in my second boundary condition, I also get 0 is equal to c2. So I found out that c2 is 0, but I found nothing out about c1. So what that means is that I do have x is equal to c1. It can be some arbitrary constant c1. And this represents an eigenfunction, because I did get a possible answer for my capital X. Now, the corresponding eigenvalue for this is what is lambda that makes this true? Well, lambda is 0, because negative lambda is equal to 0, which means lambda is equal to 0. So what this is our eigenvalue, n eigenvalue. So what this is saying is if I take lambda equals 0 and I plug it into that lambda, then the solution to that differential equation is x can be any constant, any arbitrary constant. So we did get an answer. You need to write down an answer or they'll take off points. But I don't really care about that. That's not a very interesting answer. So we continue on to our case 2 and then eventually our case 3. So we have our case 2. And in case 2 I say, what if everything underneath this square root is positive? So if negative lambda is greater than 0, which means I'm going to set negative lambda equal to alpha squared. Because then I can plug this in for my m, and I said that I have m is equal to plus or minus the square root of alpha squared, which means that my m is equal to plus or minus alpha. So now this is the situation where I have non-repeating real roots. So the form of my homogeneous, we have capital X is equal to C1 e to the positive alpha x, lowercase x, plus C2 e to the negative alpha times lowercase x. And now this is the solution that I'm going to next apply the boundary conditions to and see, do I get values of C1 and C2 that work? So first thing that we do is we have to take our derivative because both of our boundary conditions are defined for the derivative. So when I take the derivative of this, I get capital X prime is equal to alpha C1 e to the alpha x minus alpha C2 e to the negative alpha x. I'll plug in my first boundary condition that says when my variable x is equal to 0, my function x prime is equal to 0. So I have 0 is equal to alpha C1 e to the 0 minus alpha C2 e to the 0. My e to the 0s both go to 1. I end up getting alpha C1 is equal to alpha C2, which tells me that C1 is equal to C2. Cool. Now let's plug in the second boundary condition. And that says that when my variable x is equal to 4, my function is equal to 0. So I have 0 is equal to alpha C1 e to the 4 alpha minus alpha, and instead of C2, I'm just going to write C1, e to the negative 4 alpha. So I now have this equation. So I'm going to move one to the other side. So we have alpha C1 e to the 4 alpha is equal to alpha C1 e to the negative 4 alpha. And I see that my alphas can divide out. And I know that there's no value of alpha that can make the left side equal the right side. So the only possible way that this can work is if my C1 is equal to 0. So I have C1 has to be equal to 0. And if C1 is equal to 0, that means C2 is also equal to 0. And I have no eigenvalues because this is the trivial solution. So we end up getting no eigenvalues. But that doesn't surprise us because we know case 3 is where all the magic happens. So let's move on to case 3. And in case 3, I say everything underneath the radical, yes.
In the last problem, did you get an eigenfunction or eigenfunction?
So you're saying with this part? No. So when we have no eigenvalues, there's no eigenfunctions either. Because there's nothing that I can, there's no function that's a result that results. Yeah. So because when we got to this situation where my capital X was just equal to C1, that is, I'm looking for a function that works. And C1, I didn't get to be 0, I didn't get to be any value, so that means it can be any arbitrary constant. So I do have a function that works. Well, that is alpha, or X is equal to C1. And I have to see what is the corresponding lambda value that makes that equation happen. And the corresponding lambda value that makes that equation happen, we look to our start of case 1, and we said that negative lambda is equal to 0. Or in other words, lambda is equal to 0. So when we plug in lambda equals 0, we get a solution. So when I plug in lambda equals 0 to that lambda, I get a solution of, if I have x that is any constant, the equation is true. Are we ready to jump into case 3? Let's go. So we say that everything underneath the square root, negative lambda, is going to be now less than 0. So I'm going to set my negative lambda equal to negative alpha squared, which means that m is equal to plus or minus the square root of negative alpha squared, which means that m is equal to plus or minus alpha I. So now we have imaginary. Put it in the format of our imaginary, which is capital X is equal to e to the 0x times C1 cosine, no, let me do sine, C1 sine of alpha x plus C2 cosine of alpha x. And I know that e to the 0x is just going to go to 0. And the reason we have 0 is because I have n is equal to 0 plus or minus alpha I. So that 0 comes down to this exponent. Yeah?
Is there any reason you chose to put sine first?
Now, I forgot. Do I normally put sine or cosine first? It doesn't matter the order. So we have x is equal to C1 sine of alpha x plus C2 cosine of alpha x. Now, just like we did with case 1 and case 2, let's plug in our boundary conditions. So the first thing I have to do is take my derivative. So we have capital X prime is equal to, we get alpha C1 cosine of alpha x minus alpha C2 sine of alpha x. So that's just taking the derivative to get here. Now we have to plug in the actual boundary conditions. So the first condition is when my variable x is equal to 0, my function x prime is equal to 0. So I have 0 is equal to alpha C1 cosine of 0 plus minus alpha C2 sine of 0. Well, I know that cosine of 0 goes to 1, and I know that sine of 0 goes to 0, so that whole thing goes away. 0 is equal to alpha C1. I know that alpha can't be 0, so I know that C1 has to be 0. So now we plug in our second condition. And I have 0 is equal to alpha C1 cosine of 4 alpha minus alpha C2 sine of 4 alpha. And I know that from my first boundary condition, C1 is equal to 0. So that whole first term goes away. So I'm left with 0 is equal to negative alpha C2 sine of 4 alpha. Now I know that alpha can't be 0, so I can basically drop that out, because that can't make the equation true. I really don't want C2 to be 0, because if it is, then C2 0, C1 0, I have a trivial solution again, and I figure out nothing, and I'm going to get the problem wrong. So I'm going to say, well, that can't be 0. So that means I need to have 0 equal to negative sine of 4 alpha. Or, I mean, you can just divide out this negative and say that you need sine of 4 alpha to equal 0. What values does alpha have to be to make that true? Well, for that, I like to draw my unit circle. So I know that sine in my unit circle represents the y value. So I know that my sine is 0 when I'm here, or here, or here, or here. So that means when I'm at 0, or pi, or 2 pi, or 3 pi, or any multiple of pi. So that means I know that sine of n pi is equal to 0 for n is equal to 0, 1, 2, dot, dot, dot. Do we all agree with this? That sine of n pi is equal to 0. Well, I need sine of 4 alpha to be equal to 0. So let me set 4 alpha equal to n pi. So we have 4 alpha is equal to n pi. And I'm trying to find out what is alpha. So I can divide over this 4. And I get alpha is equal to n pi over 4. But that's great. But I don't care what alpha is. I made up alpha at the start of this problem. I want to know what lambda, excuse me, I want to know what lambda is. I want to know what are my eigenvalues. So I can just take this and plug it back into this equation where I define what the relationship between alpha and lambda. So I can say that negative lambda is equal to negative alpha squared, which means negative lambda is equal to negative n pi over 4 squared. Just divide out the negatives, and we get lambda is equal to n pi over 4 squared for n is equal to 0, 1, 2, dot, dot, dot. So what these represent, I found all of my values for lambda, and these represent my eigenvalues. And once I find those, I want to know, well, what are the functions that are the solution to the differential equation for each of these eigenvalues? And the way that we find that is we look at, well, what's the solution to the differential equation in case 3? Well, right here is my case 3 solution. So I know that C1 is 0 because I showed it right there. So this whole term can go to 0. And all I'm left with is x is equal to C2 cosine of alpha x. So let's plug in my alpha, and I'll have my eigenfunction. So we have x is equal to C2. I never found out what that was, so it can still be any constant. So I'll leave that as C2 cosine of alpha, which is n pi over 4 times x. And this is again for n is equal to 0, 1, 2, dot, dot, dot. Cool. So now I did all of this, and why did we do all of this in the first place? Well, I'm still just trying to move to the next step right here. That's all that I'm trying to do. I'm trying to get a function of what x is equal to. Well, I finally got that function of what x is equal to. So I can take this and bring it down right over here and say that my function x is going to be equal to some constant C2 times cosine of n pi over 4 times x, as long as n is equal to 0, 1, 2, 3, dot, dot, dot. Yay. So now we're one step closer to the end. Yeah.
It should be squared, right?
No, because right here, C2 cosine of alpha x, I'm plugging in alpha, not lambda.
Okay, why don't we solve this?
Because, yeah, The question was, why do we solve for lambda? You'll see that in the next step, because I still need to know what my lambda values are just so I can plug it in here. Yeah?
Can you briefly real quick, like the step from eigenvalues to x?
So how did I get this? So when I found my eigenvalues, I said, I actually have values that make this problem work. Now, I want to know what is the solution to the differential equation for each of these eigenvalues. All that an eigenvalue is saying that I can pick one of these values. So pick any value of n and plug it in here. So choose n equals 1. We plug in, we get 1 pi over 4 squared. If I were to take that value of pi over 4 squared and plug it into this differential equation, what this is saying, since I got an eigenvalue, it's saying you will get an answer if you plug in that value of pi over 4 squared. If you can't plug in any arbitrary number and get an answer. But it's saying that these are the specific numbers that you can plug in to get an answer. But then the next question to that is, what is that answer? And that answer is represented by your eigenfunctions, which we know come from right here because this is my function x in my case 3. And all that I have to do is plug in what I don't know. Well, I need to figure out what that alpha is. Well, I solved it right there, so I plug in, and this represents my eigenfunctions. Are there any questions about how we got to this point? Yeah. So the question is, do we just disregard that x equals c1? It is absorbed within this solution because for n equals 0, I plug in 0, I get cosine of 0 is 1, and all I'm left with is x is equal to a constant. So the reason why we don't have to do anything for that, the one that we found in case 1, is because that is represented right here for our n equals 0 case. So the question was, is there ever a case where we have to do something more to account for something we got in case 1 or case 2? I don't think so. I can't imagine they would give you something where you're going to get a solution in 2 separate cases, because that would just add so much more stress to your life. Are there any other questions on how we got to this point? Yeah. All the way over here? Getting to this? So from the way we got to this was just our separation of variables. So separation of variables is the same thing that we did on test 3, where the first thing that we did was I rewrote the equation that I was given of ut equals 3 ux x in terms of x's and t's. And I divided the whole thing by u, which is capital X times capital T. Got me to this point of all of my t's are on one side, all of my x's are on the other. And at that point, I set it equal to this constant negative lambda. So that way I can write 2 separate ordinary differential equations to then go through and solve to find what the solutions to each of those equations are. Make more sense? Capital X times capital T. It's because it says it right there, top 1. Yeah. It will be. So you will always have a case, it will always be the condition that your function u is equal to capital X times capital T, because the problems that you're dealing with for this are your heat equation and your wave equation, which are both physical examples of differential equations. And in both of those physical examples, that function, which is either in your heat equation, it's the temperature, or in your wave equation, it's the amplitude of your wave. Both of those have that property where u is equal to capital X, which is your horizontal position, times capital T, which is your time. That the only thing that will ever be different from that first condition of ut is equal to 3 times uxx is that constant. That's the only thing that will ever change for your heat equation problem is that constant 3. And then your boundary conditions and initial conditions. But you will always start off, if it's the heat equation, with u sub t is equal to a constant times u sub xx. Yeah. So this graph right here, all that this is used to do is figure out what values of sine. We can fly down, guys, please. Just I want the video to be able to make sure it hears everything, so that way everyone in the future can get everything. Okay. But the reason why we just used this unit circle was because I knew that sine of 4 alpha had to be equal to 0. So what values of sine give me 0? Well, I know that sine is 0, at pi, at 2 pi, at 3 pi, and every other value of pi. So sine of n pi is equal to 0. Well, if I know that sine of 4 alpha and sine of n pi are both equal to 0, then I can set 4 alpha equal to n pi to figure out what my alpha is. Yeah?
If that was cosine, would that be pi over 2 times n?
If it was, so you're saying if this was cosine instead, then we would just have to say, well, I know that my cosine is equal to 0 up here and down here. So this is pi over 2, 3 pi over 2, 5 pi over 2. So in that case, we would have the cosine of, I know it's going to be an odd number times pi over 2. So we like to write that as 2n plus 1 times, 2n plus 1 over 2 times pi is equal to 0. 4n is equal to 0, 1, 2, dot, dot, dot. So if it was cosine having to equal 0, instead of just being n pi, it's now 2n plus 1 over 2 times pi. Yeah. It has to be any value of n that's a whole number. So I can't just pick 1.5 because 1.5 pi is somewhere over here where sine would be 0. I don't know for 100% sure, but I'm going to assume it has something to do with the fact that t has to be greater than 0. I just remember that if you always take whole numbers, so 0 and up, because yes, theoretically, sine of negative 1 pi would be equal to 0, but we only use n values that are whole numbers. I don't know the exact reason, but I'm going to assume it goes back to that x has to be greater than 0 and t has to be greater than 0. Yeah. It's going to be with your initial condition, so we haven't even gotten there yet. And we'll go one more problem before I finish this one up. Yeah. We'll do that before the weight equation. I'll explain more about like the physical parameters. So now I'm going to go through, we're actually going to do the last step of this problem. So far we've done the separation of variables, and we've done the eigenvalue problem. But now we actually need to put everything together to get a solution. So I've used my equation, I've used my boundary conditions, now it's time to use my initial conditions. So, let me go over here. Since I now have a solution for t, and I have a solution for x, I can put those together to for the first time find out what is my function u. So I know that u is capital X times capital T. So I know that my u is my capital X, which is going to be C2 cosine of n pi over 4x. And this whole thing is going to be multiplied by t, which is C1 e to the negative 3 lambda times t. And again, one thing that I can plug in, because I now have values for lambda. I found them right here in my case 3. So I can now take this lambda of n pi over 4 squared and plug it into the lambda that I had in my t. So u is equal to, and notice that I have two constants, c1 and c2, that are being multiplied by each other. Those are just going to become one constant. So I'll just write that as c3 times cosine of n pi over 4x times e to the negative 3 times n pi over 4 squared times t. And this is for n is equal to 0, 1, 2, 3, dot, dot, dot. To answer your question about why n has to be 0 or greater, it doesn't have to do with t's, but it has to do with right here. Because if I picked a negative value for n, I would get a negative cosine value, which would make my x not between 0 and 4. So that's your reason. So right now, I have a solution. For the first time, I actually have a value of a function u that's x times t, and I'm almost there. The very last step is I need to figure out what that constant is. Now, technically, I shouldn't have written this as c3. I should write it as c sub n, because for each value of n that I choose, I'm going to get a different constant. So if I plugged in n equals 0 for the two n's, I would get one constant. If I plug in n equals 5, I would get a different constant. N equals 17, I would get a different constant. So we have this equation. Now the last thing that I need to do is use my initial condition to figure out what those constants are. So we look at the initial condition, and it says that my function u, where x is just a variable, but t is equal to 0, it's going to equal cosine of pi over 2 times x minus 7 cosine of 3 pi over 4 times x plus 5 cosine of 3 pi over 2 times x. Yeah?
Why is the lambda, when you plug in for lambda, why is it squared there?
Because I plugged in lambda, which is n pi over 4 squared. I'm not plugging in the alpha. So I have this. Let me apply that initial condition. So it's saying u at x comma 0, which means I'm going to plug in 0 for t. This is going to be c sub n cosine of n pi over 4x. And notice that when I plug in a 0 for t, I'm just going to have e to the 0, which is just going to be 1. So u of x0 is just c sub n cosine of n pi over 4 times x. Yeah? Because these two constants are being multiplied by each other. So when you multiply a constant by another constant, you can just make that one constant. So I just rewrote that as c sub n. Yeah?
The eigenvalue for the value, how can we just disregard the first
So in case 1, the eigenvalue was lambda equals 0, right? What happens when I plug in n equals 0? I get lambda is equal to 0 squared, which is 0. So I'm not disregarding the case 1 eigenvalue. It's included in this set of n pi over 4 squared. So now, I know that u sub x comma 0 is c sub n cosine of n pi over 4x, but I know that that's also equal to cosine of pi over 2 times x minus 7 cosine of 3 pi over 4x plus 5 cosine of 3 pi over 2x. So the next step is, what this is saying is, right here I have a continuous, I have infinitely many solutions, right? Because I can pick any value of n to plug into this equation. But what this is saying is that it's going to be equal to just these three terms. So I need to figure out which values of n correspond to these three terms, because those are going to be the only values for n that are still valid for the problem after I apply my initial condition. So I need to see in this first term what value of n did I plug in. Well, let's look inside this cosine. We have pi over 2 times x. Here we have n pi over 4 times x. So in order to have n over 4 become 1/2, what does my n have to be? 2. So I know that for this term, my n has to equal 2. And therefore, what is my c sub 2? What is my constant for my n equals 2 term? Well, it's just 1. So my c sub 2 is equal to 1. Now let's do that for the next term. What's the corresponding n value for this next term? Well, I see that I have a 3 pi over 4. So I know that my n has to be 3. So my n for the middle term is 3. And therefore, my c sub 3 is equal to -7. I'll do the same thing for the last term. And for this one, I see that my n has to be equal to 6, which means my c sub 6 is going to be equal to +5. So now, this was my solution before plugging in my initial condition. But now that I've plugged in my initial condition, this is saying that the only values that I can use for n, I can no longer have it as for n equals 0, 1, 2, 3, all the way to infinity. I can only have for n equals 2, n equals 3, and n equals 6. So we can now finally write out our full solution with our boundary conditions and initial conditions all accounted for. Yes? I'm going to say no. The question was, in case 1, we have that one eigenvalue that we already accounted for. Is there going to be a situation where that doesn't happen, where we have to account for it in some other way? I can't see that happening. I don't know what way you would get that it wouldn't be a constant solution. And if it's a constant solution, it's going to be accounted for in this method. Cool. So now, let's take these initial conditions, plug them into our u, and then we're done. So, I'm going to do it over here so I have enough space. So I have u of x and t is equal to, instead of c sub n, I'm going to take my first n term, which is n equals 2, and I'm going to say that for my n equals 2 term, I know that I have the coefficient of 1, times cosine of n pi over 4x, but instead of n, I'm going to write 2. So this is going to be 2 pi over 4x times e to the -3 times 2 pi over 4 squared times t. And this whole thing is just my n equals 2 term. Now we add on our n equals 3 term. So we do actually -7 times cosine of 3 pi over 4 times x times e to the -3 times 3 pi over 4 squared times t. And this whole thing is our n equals 3 term. And then finally we have our n equals 6 term, where we do +5 cosine of 6 pi over 4x times e to the -3 times 6 pi over 4 squared times t. If you want, you can simplify our 2 pi over 4s and our 6 pi over 4s. and you probably should do that, but I'm going to leave it as it is for right now. And just so I have it all consistent, we know that this last term is our n equals 6 term. And finally, we have a solution to our to the heat equation that we wrote on that first page. And it is this whole super long thing. And we just solved one problem on our problem. What other questions do we have about this?
So what does the answer represent?
So, okay. So, one thing that I like to do, and I was going to explain this with the wave equation, but I'll explain it with this. What does this answer represent? What is the purpose of doing all of this? Well, the conditions for your heat equation, so imagine you have some metal rod and you're heating it up from one end. And you have a constant heat at that one end. What the heat equation says is I can pick any point x on that rod at any time t, and I can know the temperature of the rod at that point by plugging in any value, some value for x and some value for t. For all of my x's and t's, I will know the temperature at that given x and t. So that's the physical representation of what this heat equation means. And now, that's what's going on in the heat equation. What our boundary conditions is saying is that use of x at 0 and 4 is 0. So this is saying that the derivative in the x direction at the left end of my rod, which is 0. So imagine right here is this is our rod that we're heating. Here we have x equals 0. Here we have x equals 4. And what this is saying is that the derivative with respect to the x direction at either side is 0. So that means the temperature is not changing at either end. So the scientific explanation or the scientific reason behind that is both ends are insulated, which means no heat can transfer across this line or across that line because there's insulation there. That explains why my use of x at both ends of the rod is 0. And then we look at our initial condition, and this was a little bit more difficult to explain more practically because it is a little bit more complicated. But basically, this is some function that if I were to plot this function, I would get some weird thing with a bunch of peaks, whatever. I don't know what it looks like, but what this line would represent is what is the initial temperature of my rod. So at time equals 0, if I pick some x value, say right here, that's going to be the temperature of it. And you would figure out whatever that red line looks like by plotting or by looking at that initial condition term. So that's physically what's going on. I think it helps to add a little bit of context to know this is actually a scientific problem that we're solving, which is pretty cool. Other questions? Yeah.
Are we going to be given our initial conditions out of the equation or how to derive
So the question was, are we going to be given the examples as an initial condition, or do we have to derive it from like a work, or did you say a 4-year series? The one final exam that I have, that I'm pretty sure all you guys have as well, is it shows the initial, it basically shows the setup of the problem exactly as I drew it, where you have an equation, it says boundary condition 1, boundary condition 2, initial condition 1, and it has them all listed out like that. So I don't think you're going to have to derive it. I don't think they're going to give you anything saying it's insulated at both ends and you have to know how to set up your boundary conditions for that. I have to assume they're going to give it to you straightforward like this. Yeah. The question was, if there were to be a 4-year series in this, where would it be? It would be right here. Their initial condition, instead of placing out 3 separate terms, would just say something like,
Gio Garcia, why did you say this?
I don't even know what it would look like, but notice how these are similar to a Fourier series, right? We know that the equation for a Fourier series is like b sub n cosine of n pi x over L. It's pretty close already. The only thing that it would do is it would give you something for this b sub n that you then had to figure out, okay, what's my general b sub n, as opposed to just saying n is equal to 3. Question? Any other questions on the heat equation? Cool. I'm going to take like 5 minutes to erase all 6 boards because I somehow used all of them for this problem, and then we'll get started on the wave equation.
Sorry, I'm not trying
Alright, nothing's going
We're starting in strictly tofu and like.
Are we ready for the wave equation? So the next thing we have is the wave equation. So the first thing I'll point out is what's different now from our heat equation. And obviously everything's set up a little bit different. We have different boundary conditions, different initial conditions. But what fundamentally is different. Notice how in the last problem we had a u double x, but our u, when we took the derivative with respect to t, it was only a single derivative. Now we have a second derivative with respect to time. We still have two boundary conditions, but now we have, and last time we had an initial condition that looks similar to that, but now we have a second initial condition. And the reason why we need that second initial condition is because we now have two derivatives with respect to t. So we're going to have another term that we have to solve for in that t. So those are the only things that really change. We're going to be doing the same steps, just at one point we have to incorporate one extra step involved because we have an extra initial condition. This is going to look a lot more complicated as we're going through, but it's not going to be that bad. Trust me, please. The other thing is, I don't have the solution written out to this. I did this problem in the review last year, and I guess I just never wrote down the solution for it. I just wrote down the problem. So we're going to be solving it together. But on the good side is, that first problem, I didn't look at my notes one time, and we did get the right answer. So, that's a good thing. But this is the equation that we're starting with. A quick 2 seconds of what this physically means is, you guys might have done an experiment like this in high school and if you took physics, where you have a string that's stuck between two poles, and on one end you vibrate the string up and down, right? And it forms some waves in the string. Well, that's what the wave equation is. What it's saying is, at some position x along the string, and at some time t, what is the amplitude of that string? And that's what this u gives us. And our boundary conditions are saying that at my x equals 0, my amplitude is always 0, so that means it's fixed. And the derivative of x at 1 is 0, which means that the velocity at the far end is always constant. Or the velocity at the other end is always 0. Yeah. And then our other initial condition, this says what does the wave look like in the string at my initial time of t equals 0, and this is saying that at my time equals 0, I believe this is saying my velocity is 0. So it's starting stationary, starting not moving. You don't need to know what that all means, but that just gives some scientific context that this is an actual problem that we're solving. So let's jump into solving. Who remembers what the first step that we did in our heat equation was? Separation of variables. So let's do that. So the first thing I want to do is I want to rewrite this so that when I don't have u, I just want my capital X and my capital T. So I'm going to have capital X double prime times capital T minus 16 times capital X capital T double prime is equal to 0. Now, before I even start dividing by my u, I want to just put these on separate sides. So that way I have one term on one side, the other term on the other. So we have x double prime times t is equal to 16 capital X capital T double prime. So now that I have this, now I'm at the step where I divide everything by my capital X capital T. My t's go away on the left, my x's go away on the right. And I have capital X double prime over capital X is equal to 16 capital T double prime over capital T. And again, we have this question of, do I want the constant in the numerator or do I want it in the denominator? And just like in the last problem, we want to get it in the denominator so that way we have our double derivative by itself. I don't want to have a coefficient in front of my T double prime. So I'm going to divide over this 16 to be a coefficient in front of my capital X. And now that I've done that, I can set it equal to negative lambda. And I can now write my two ordinary differential equations from here. So the first one that I'm going to have is capital X double prime plus 16 lambda capital X is equal to 0. And then my other one is capital T double prime plus lambda capital T is equal to 0. So now, in the last problem, we said, okay, let's solve the easy one first, the one that was only a first order, because we could get the answer to that easily. But now, we don't have an easy one. Both of these are second order. So where do we start? Well, in order to move forward, we look at our boundary condition. Because I know that the next step from now is going to be my eigenvalue problem. And in my eigenvalue problem, I need to apply my boundary conditions to help me solve. So I need to look at my boundary conditions and say, which equation, my x's or my t's, does that boundary condition, do the boundary conditions apply to? And we see that in both of those cases, they apply to our x. Because in both of my boundary conditions, I'm plugging in a value for my x. So I need to go into my x equation first. And this is where I'm going to be doing my my eigenvalue problem. So let's do that. So I'm going to be jumping right in. Let's find our homogeneous solution. So it's going to be our auxiliary equation of m squared plus 16 lambda is equal to 0, which means m squared is equal to negative 16 lambda, which means m is equal to plus or minus the square root of negative 16 lambda. And I can actually pull out a square root of 16. So I have m is equal to plus or minus 4 times the square root of negative lambda. Cool. And now we start our eigenvalue problem. So again, I'll do it over on this board, and again, I'll do it in blue. So we start off with case 1. And for case 1, I say, what if everything underneath the radical is equal to 0? Well, that means I have m is equal to plus or minus 4 times the square root of 0, which means m is equal to 0, which means my capital X is C1 e to the 0x plus C2x e to the 0x, or rewriting it, we get x is equal to C1 plus C2x. Same exact steps as we had for the last problem. Plug in lambda equals 0, we get m equals 0, and then we have our x is equal to C1 plus C2x. Next thing we need to do is we plug in our boundary conditions. And we notice that one boundary condition is defined with just u, or just our function x. The other boundary condition is defined with x prime. We have that u sub x. So I know that I'm going to have to take my derivative, so I might as well do that right now, and then we'll plug in our boundary conditions. So I take my derivative, x prime, I get it's just equal to C2. Nice, easy derivative. So now we plug in that first boundary condition, and what that says is when my variable x is equal to 0, my function x is also equal to 0. So function x is equal to 0 is equal to C1 plus C2 times 0. That gives me C1 is equal to 0. I look at my second boundary condition. It says when my variable x is equal to 1, I don't even have anywhere to plug that in. It says my derivative of x, my x prime, is equal to 0. So I get 0 is equal to C2. In this case, I get C1 and C2 are both equal to 0, which means this is the trivial solution. So I have no eigenvalues. So in this question, we don't even have that constant that we may or may not have to worry about later. We just get no eigenvalues straight up. What's next? Case 2. Very good place to proceed. So we have case 2. And in case 2, our negative lambda is going to be greater than 0, which means negative lambda is equal to alpha squared. So I take that alpha squared, I plug it in for my m all the way over there, and I have m is equal to plus or minus 4 times the square root of alpha squared, which means m is equal to plus or minus 4 alpha. I have real non-repeating roots, so my capital X is equal to C1 e to the 4 alpha x, 4 alpha x, plus C2 e to the negative 4 alpha x. Just like I did in the last step, the next thing I'm going to do is take my derivative and then plug in my two boundary conditions. So I take my derivative, x prime is going to be equal to 4 alpha C1 e to the 4 alpha x minus 4 alpha C2 e to the negative 4 alpha x. Now I can plug in my boundary conditions. My first boundary condition says when my variable x is equal to 0, my function x is equal to 0. So I have 0 is equal to C1 e to the 0 plus C2 e to the 0. Therefore, I have 0 is equal to C1 plus C2, or C1 is equal to negative C2. Now I can plug in my second boundary condition. And for my second boundary condition, it says that when my variable x is equal to 1, my derivative of x is equal to 0. So I have 0 is equal to 4 alpha C1 e to the 4 alpha times 1 minus 4 alpha. Instead of C2, I'm going to plug in a negative C1. So it's just going to be plus 4 alpha C1 e to the negative 4 alpha times 1. So at this point, I'll move 1 again to the other side. So I have 4 alpha C1 e to the 4 alpha is equal to negative 4 alpha C1 e to the negative 4 alpha. My alphas and my C1s can divide out. My 4 can divide out. And I'm left with e to the 4 alpha is equal to e to the negative 4 alpha. So the only way that the left side can equal to the right side is if these C1s were equal to 0. It's the only way that that can be true. So therefore, C1 is equal to 0. And since C1 is equal to negative C2, C2 is also equal to 0. Which means that, again, I have no eigenvalues. Now we get to do the fun one. So in case 3, I say that my negative lambda is now going to be less than 0, which means negative lambda is equal to negative alpha squared. So my m is plus or minus 4 times the square root of negative alpha squared, which means m is equal to plus or minus 4 alpha I. And if that's what my m is equal to, then I know that my solution, since this is imaginary, my capital X is going to be C1, e to the 0x times C1 cosine of 4 alpha x plus C2 sine of 4 alpha x. And I know that my e to the 0x is just going to go to 1. So now that I have this, just as I did in case 1 and case 2, I'm going to take my derivative and then plug in my conditions. So let's take the derivative, and we'll write it up here, capital X prime. The derivative is going to be a negative 4 alpha C1 sine of 4 alpha x plus 4 alpha C2 sine of 4 alpha x. Cosine, thank you. So now that I took my derivative, it's getting very repetitive. Now I plug in my boundary conditions. So I look at my first boundary condition, and it says that my function x is equal to 0 when my variable x is equal to 0. So I have 0 is equal to C1 times cosine of 0 plus C2 sine of 0. I know that sine of 0 is 0, so that goes away. I know cosine of 0 is 1, so I get C1 is equal to 0. I now look to my second boundary condition, and I know that my function x is equal to 0 when my variable x is equal to 1. So I'm going to have 0 is equal to negative 4 alpha. For C1, I'm just going to plug in 0 right away. And we're going to have sine of 4 alpha times 1 plus 4 alpha C2 cosine of 4 alpha times 1. So this whole first term goes to 0 because I have a 0 in there. And I'm left with 0 is equal to 4 alpha C2 cosine of 4 alpha. Now, I know my 4 can't be 0, so I can ignore that. I know that my alpha can't be 0, so I can get rid of that. I know that I really don't want C2 to be equal to 0, because then once again, I have a trivial solution. So I'm going to say that 0 has to be equal to cosine of 4 alpha. So now, my question is, what values does alpha have to be in order to make this true? So now we get to go back to our unit circle. I'm going to draw it in the same exact place that I drew it last time. So we have our unit circle. And now I know that cosine corresponds to the x value. So I know that cosine is equal to 0 at the top and the bottom. So this is pi over 2 and 3 pi over 2 and 5 pi over 2 and 7 pi over 2. And basically every odd number times pi over 2. So how can I write that in terms of n? Well, I know that I can write that as 0 is equal to cosine of an odd number. I can write as 2n plus 1 divided by 2 times pi. And this is going to be 4. N is equal to 0, 1, 2, dot, dot, dot. Because if I plug in n equals 0, I'm going to get positive 1 over 2 times pi, which is that first case. If I plug in n equals 1, I'm going to get 3 over 2 pi. Then I'm going to get 5 over 2 pi and 7 over 2 pi. So I know that cosine of 2n plus 1 over 2 times pi is equal to 0. And I know that cosine of 4 alpha is equal to 0. So therefore, I can take this 4 alpha and set it equal to 2n plus 1 over 2 pi. And again, I'm trying to solve for my alpha, so let's divide over that 4. And I get alpha is 2n plus 1 over 8 times pi. But just like in the last problem, I don't care what alpha is really. I want to know what is my lambda. So I can take this and plug it in up here for where I define lambda. So negative lambda is equal to negative alpha squared, which means negative lambda is equal to negative 2n plus 1 over 8 pi squared. Only thing I have to do, divide out the negatives, put a box around it, and then what do these represent? My eigenvalues, yes. And I have to remember to write for n is equal to 0, 1, 2, dot, dot, dot. So these represent my eigenvalues. So now what are the corresponding eigenfunctions? Well, I look in my case 3 to see where's my function x. And my function x is right here. Well, I already found out that C1 is equal to 0. This whole term can go to 0. And now I can plug in right here with the value of alpha that I now found. So my capital X is going to be equal to C sub n times sine of 4. Now alpha, I'm going to plug in this. So 2n plus 1 over 8 pi times x. And you can simplify this a little bit with your 4 and your 8, so let me do that. So we have x is equal to c sub n sine 2n plus 1 over 2 pi times x. And these are your eigenfunctions. Make sense? This one? Because I know that 0 is equal to cosine of 4 alpha. And from looking at my unit circle, I know that 0 is equal to cosine of 2n plus 1 over 2 pi. So I can set 2n plus 1 over 2 pi equal to that 4 alpha to solve for alpha. Yeah. Not yet. I mean, the idea is still that for each value of n, your constant's going to be different. They probably won't take off points at this point, just as long as you write it as Cn in your final answer. So now, we did all of this to figure out what's our function of x. That's a solution. Just so I can bring it back over here and say that x is equal to c sub n sine of 2n plus 1 over 2 pi times x. So now we're halfway done. But just like when we did the first problem, halfway done wasn't really halfway done. This time we're more than halfway done with the steps of solving. But I have half of my final solution of my u is equal to capital X times capital T. Now I look to my second order differential equation. And how do I solve this? Well, I solve this by saying m squared plus lambda is equal to 0, which means m squared is equal to negative lambda, which means n is equal to plus or minus the square root of negative lambda. And now you might be looking at me and saying, oh God, we have to do 3 more cases? No. Because I already know what lambda is. Right? That's super cool. We have it right here. That's also why we solved for x first. Because x allowed us to find our eigenvalues that I can now take these and plug it right in here. So now we have this. We have m is equal to plus or minus the square root of negative 2n plus 1 over 8 pi squared, which is nice because I have the square root of something squared. So my m is going to equal to plus or minus this whole thing, so 2n plus 1 over 8 pi times I. So right here, this is already telling me I know which case of my homogeneous this fits into, because I got imaginary solutions. So I can fit that directly into my format for imaginary solutions. So my capital T is going to be equal to e to the 0 t times C1 cosine of this whole thing, 2n plus 1 over 8 pi t, plus C2 sine of 2n plus 1 over 8 pi t. So I know, again, my e to the 0 t is going to go to 0, and I'm left with this function of t that's a little bit long. I'll just leave it there. But we have C1 cosine of 2n plus 1 over 8 pi times t, plus C2 sine of 2n plus 1 over 8 pi times t. And now, I covered it up, but now we're at the point where we used this in our separation of variables. We used our boundary conditions to find our eigenvalues and our eigenfunctions. Now, all that we have left to do is use our initial conditions. So I have an equation for x, and I have an equation for t. So I can find my equation for u by multiplying the two of them together. So I have u is equal to capital X times capital T, which is C sub n times sine of 2n plus 1 over 2 pi x times C1 cosine of 2n plus 1 over 8 pi t plus C2 sine of 2n plus 1 over 8 pi t. So now, to simplify my constants a little bit, because I see, well, I don't see because I have it covered up, but we know that we have two initial conditions. So therefore, I can solve for two constants. But right now, it looks like I have three. Well, I know that when this gets multiplied by each of these, those constants are going to be absorbed a little, right? Because it's going to be our Cn times C1 and Cn times C2. So instead of writing out as three different constants, I'm just going to get rid of this C sub n, and I'm going to say that C sub 1 is turning into, we'll call it B sub n, and we'll call this D sub n, our C2. So I know that there's still going to be some constants, but they're going to be different for every value of n. So let me just multiply this C sub n through, so that way we're only dealing with two sets of constants. Now that I'm here, we need to look at our initial conditions. So I know that our first initial condition is u, since I have it covered up, I got to look back at the notes. It says that u at x0 is going to be equal to negative 6 sine of 3 pi over 2x plus 13 sine of 11 pi over 2x. So before I write that down, let me evaluate this for what I have. This is saying u of x comma 0. That's going to be sine of 2n plus 1 over 2 pi x times, now I'm plugging in 0 for all of this, it's going to be b sub n cosine of 2n plus 1 over 8 times pi times 0, so cosine of 0. And it's going to be plus d sub n times sine of 0. Well, I know that my d sub n term goes away. I know that my cosine just turns to 1. And my u of x 0 just becomes b sub n sine of 2n plus 1 over 2 times pi x. And I can now say that this is equal to what was given in that initial condition, which was negative 6 sine of 3 pi over 2x plus 13 sine of 11 pi over 2x. Now, does this step look familiar? Because this is exactly what we did in the first problem when we applied our initial condition. We have some function with n's and a constant, and we have two different terms that I now need to figure out some way to relate these. And what this means is I now need to figure out what value of n corresponds to this solution, what value of n corresponds to this solution, and those are going to be the only two values of n that apply for this problem. It's no longer going to hold that my solution is 4, n equals 0, 1, 2, 3, 4, all the way up. So let's do that. I look at this first term, and I need to see what's my n value going to be. So what value of n do I plug in that gives me a 3 pi over 2? Well, n is equal to 1. So I plug in n equals 1, it's going to give me 2 times 1 plus 1, which is 3 over 2 pi, which is what I want. And my my b sub 1 is going to be negative 6. And then I come over here to my second term, and I see that my n is going to equal 5, because that's what's going to give me an 11 pi over 2. And my b sub 5 is equal to 13. So I've now solved for the two possible constants that I can have for my b term. So now I need to apply my second initial condition. And I'm going to come over here for that. The first thing that I'm going to do is let me write out my full answer now with this. You know what, I'm not going to write out the full answer just because that's going to be super, super long. Now, you know what, let me write it down just so you guys don't be confused. So now, after I figured out these B1 and B5, I have another version of my answer that's a little bit closer to being done. So U is capital X times capital T, which is now equal to, so looking at this line, it's going to be sine of two times n, but my first n is going to be 1. So 2 times 1 plus 1 over 2. So this is going to be 3 over 2 pi x times negative 6 cosine of 3 pi over 8 times t plus it's going to be now d sub 1, right? Because my n is equal to 1, so it's d sub 1 times sine of 3 pi over 8 t. So all of this is my n equals 1 term. Yeah, now I get to do my n equals 5 term. So plus sine of, it's going to be 11 pi over 2x times my b sub 5 is 13 times cosine of, when I plug in n equals 5 right here, it's going to be 11 pi over 8 times t. So cosine of 11 pi over 8 times t plus d sub 5 sine of 11 pi over 8 times t. And this is my n equals 5 term. Nice and long, right? Now you know why they didn't give you 3 terms like they did in the first one. So this is nice and super long, but guess what? We're not done yet. We get to apply our second initial condition. So we've now applied this first initial condition. Now we have to apply the second one. And for the second one, it says we have to take our derivative with respect to t. Yeah. So the good thing is, I know that my sine terms are going to stay the same, right? Because those are only with respect to x. So now I'm going to find u sub t, which is x is equal to capital T, or which is x times capital T prime. So I now take the derivative. And I have sine of 3 pi over 2x times the derivative of, so I could skip steps and make it quicker here, but I'm not because you guys are going to get confused. So I'm not going to skip steps. So I take the derivative of this, and I'm going to plug in, the derivative is going to be a sine of 3 pi over 8 t. The coefficient is going to be a 6, so it's going to be an 18 pi over 8. Because it's 6 times 3 pi over 8, so it's going to be 18 pi over 8. Well, when I take the derivative of cosine, it becomes a negative sign. So that's why the negative is gone. Plus, this is going to be a 3 pi over 8 d1 times cosine of 3 pi over 8 t plus sine of 11 pi over 2x times 11 times 13 is 143. So we have 143 times pi over 8 sine of 11 pi over 8 times t. We have a negative in front of that coefficient. That's the derivative of cosine is a negative sign. Plus 11 pi over 8 d5 cosine of 11 pi over 8 t. So now what I was saying before was I can skip steps. I know that the derivative of both of these cosine terms is going to be a sine term. And my next initial condition says plug in 0 for t. So I knew right off the bat when I was taking the derivative that I could have just dropped these derivative of cosine terms to 0, because when I plug in 0 inside this sign, the whole thing's going to go away. So if you could pick up on that, you could save yourself a couple minutes writing out this, and save a couple trees in the Amazon rainforest from writing out this entire thing. But now I can plug in ut at x comma 0, and I can plug in 0 for all my t's. So I have sine of 3 pi over 2x times this whole thing is going to go to 0. So I'm going to have 3 pi over 8 d1 cosine of 3 pi, rather cosine of 0, plus sine of 11 pi over 2x times this whole thing's going to go to 0. So we have 11 pi over 8 d5 times cosine of 0. So we have u of t, x, and 0 is equal to, I know that my cosine are just going to go to 1. So I'm going to have 3 pi over 8 d1 sine of 3 pi over 2 x plus 11 pi over 8 d5 sine of 11 pi over 2x. And I know that this is going to be equal to 0. This really bothers me. Because the only way that we can get either a relationship between the two, or they're both 0. So we'll set them the two sides equal to each other. So we have 3 pi over 8 d1 sine of 3 pi over 2x is equal to negative 11 pi over 8 d5 sine of 11 pi over 2x. No, because I know that this is equal to that, because I can say that, and this is just a way of simplifying. I know that 3 pi over 2, if I add a multiple of 2 pi to this, then I know it's just going to be the same exact value. So 3 pi over 2 plus, 8 pi over 2 is equal to 11 pi over 2. But I know that this is the same thing as saying 4 pi. So 3 pi over 2 plus 4 pi is equal to 11 pi over 2. So that means that the sine of 3 pi over 2 times x and the sine of 11 pi over 2 times x are the same thing. So these can divide out. Because they're going to end up equaling the same thing. And then my pi over 8 can divide out. And I have d1 is equal to negative 11 over 3 d5, which isn't good because that means I'm still missing a condition. So either I didn't write down the full problem, or I don't think we messed anything up.
How about I just did that and ask you will answer it. Hopefully, it really confused us.
We're definitely actually in a way.
Oh yeah, if not multiple. Did he really take that long to go through?
No, not when you.
I feel like the wave would take a long time.
No, it's still not 11 pi over 2 because 11 pi over 2 comes from our x.
Do you want to?
So, what I'm assuming happens, I didn't write down the full problem because we should need another initial condition to solve because we do have two unknowns. So, what I'm going to do is I'm just going to say that I probably just,
Let's get Kobe's making sure.
so kind of bring it back a little bit. I mean, all of this stuff is true, and there does have to be some way that we can apply this condition to actually get an answer. But it's not worth me taking you through all of that algebra to do. So the one thing that, you know, if I was to do this problem, I wouldn't have solved it this way. I wouldn't have gone through all these steps. I wrote out all these steps to show you the full picture of what's going on. So that way you can see that, okay, we now have a full solution. Now we're taking the derivative with respect to t, and we're applying that second initial condition. If I was to do this problem and solving it on my own, I would have plugged in my second initial condition to right here. Because what this second condition is saying is my x doesn't really matter. The only term that matters is my t. So this is a way that you can focus on just your t values for that second initial condition. And when you do that, things become much simpler because that's what's going to happen. Because when we do that, I can still plug in that initial condition to this value of t. So I can take my derivative, so my t prime is going to be negative 2n plus 1 over 8 pi times sine of 0 plus c2, or sorry, plus 2n plus 1 over 8 c2 sine of 2n plus 1 over 8 pi or 0. And again, it should be cosine. This should be cosine. This is just going to be 0, and I should also have pi. And when we do this, we see that this whole first term goes to 0, and this goes to 1, which tells me that t prime, which is 0, is equal to 2n plus 1 pi over 8 times c2, which gives me the condition that c2 is equal to 0. Now I never find out anything about c1, which notice is the same thing that we had over here. One of my conditions is arbitrary. But I know that this does tell me that c2 is 0, so I know that that isn't going to be included in the solution. So now my t function is just this with still some arbitrary c, but now that c can be any constant, and the solution will still hold. So I've officially run out of chord space, but I'll write the final solution right here, which is our u of x and t is equal to my x, which is sine of, well, actually I should write it out with all of my n's plugged in. So you know what? I'm just gonna erase this stuff. So what this is saying is, this is still my n equals 1 term, but I now found out that with my n equals 1 term, let me just write it over. So I'm going to rewrite it right here. So we are going to have u of x and t is equal to, with my n equals 1 term, we have sine of 3 pi over 2 times x, and now my t is just this arbitrary constant, so we're going to have just, I'll leave it as just constant c cosine of 3 pi over 8 times t plus, now it's my n equals 5 term, and I'm still going to have some constant, but it's going to be some different constant, so I'm going to write it as d. So it's d times, is it a different constant? No, it's going to be the same constant, so I'm going to write that as c again. Sine of 11 pi over 2 x times cosine of 11 pi over 8 times t. And this is my n equals 1 term. This is my n equals 5 term. And we finally have our final solution for our wave equation. Now, before everyone gets up to leave, I'm just going to say one last thing quick. If you guys have been to my reviews in previous semesters, you know that I normally do this at the end of the semester. I don't get paid for these reviews, nor do I want to get paid for these reviews. I do them because I have an unhealthy obsession with differential equations, and because I like to give back to people. But at the same time, a lot of people have said that they have expressed their thanks to me and they've offered to pay me. So I'm going to give you the opportunity to do that, but I don't want any of your money. What I will give all the money to is Stevenson. So I'm a morale captain for this year's next spring Stevenson, and what it is it's a dance marathon that raises money for children's specialized hospitals to help pay for the treatments and help the families pay for the treatments for those children that have disabilities that have to go to those hospitals. So if anybody wants to express their thanks to me monetarily, I'll write my Venmo up on the board. Feel free to Venmo me. It's absolutely not required at all, but nothing is too small or too large, and I would very much appreciate it. And I'll then donate all that money straight to those children's specialized hospitals, so that way we can help those kids get some treatment. Thank you very much. I hope you enjoyed. Have a good night, and good luck studying.